It's like week 14, right? We're so back. Weekly meeting, you know the vibes. We're going to go through this because we are running behind schedule. Come on. Announcements. Please join the Discord. I would assume everybody in this room has joined the Discord, right? Thumbs up. We're gaming. Okay. I'll give you guys a few seconds to scan the QR code. Thank you, Chase K. All right. Next. Please sign in. And is sign up up? Is signing up? Are we good? Okay, I'll give it a second. It's oh so quiet. It's oh so quiet. Is signing up now? Okay, why are they laughing? Is it signing up? Okay, I need you guys to sign in like now or else. Alright. Please check the calendar. Oh, you better be signed in, Chase K. Oh, yeah. Check the calendar. You know, that's how you stay up to date with everything. QR code, scan that, please. Also, sign up for the mailing list. That's how you stay up to date with our nice, sweet weekly newsletters. Okay, Mr. Brad. Okay, we'll give him a second. He's fiddling.
Okay, so this week we had someone propose some changes to the Constitution in just a few minutes, and by a few I probably mean 5 to 10. Sorry, we had to deal with a whole lot of issues, so I'm a little bit behind schedule. So in about 5 to 10 minutes I'll be posting the new PDF version of the Constitution. Modifications have been made. A small summary of the changes made will be provided. Similar to last time, you can go in the GitHub repo and view the exact modifications in the pull request, yada, yada, yada. I think you guys know the deal from last week. Even if you really don't care about the Constitution change, I heavily recommend that you at least just browse through it. It's really good to know kind of where we came from and what our founding documents are to really understand what RITSec is and why we do what we do. So I will be posting at 5 to 10 minutes. We will start the process over again 1 week till you have till next Friday. And at the end of next Friday, if there are no proposed changes, no proposed vetoes, the Constitution will pass and we will merge it in and it will be officially V2.1. Otherwise, if you would like to propose a full veto of the Constitution, you need to let eBoard know, specifically Max or myself. Next week, then we will hold a vote. 3/4 majority will yeet the whole Constitution modifications. If you have changes that you would like to propose, you can also propose those to Max and myself. Preferably, like, everyone do them as soon as possible instead of like later in the timeline. I appreciate it. Thank you.
Thank you, Mr. Brad. We'll continue now. Denji Mod is not here, but I'll do the announcement for him. So Team Contagion LACTF. It's an annual Capture the Flag event hosted by ACM Cyber at UCLA and fraternity Phi Beta Rho. It's open to all skill levels of security, and it's running from February the 10th to Sunday the 12th. There will be food. Please scan the QR code. There's another one. We good? Oh, we're gaming. There's another one. So this one started earlier this week. It's Team Contagions Mentor High School CTF Challenge. Valentine's Day edition, so you know it's special, right? 2-week long CTF. Apparently it's beginner friendly, like very beginner friendly, so please do that. Team Contagion goes hard. Yeah. Few know, but everyone knows. Alright. Big if true. Mr. Malik, do you have any words? Okay, Ops program is now recruiting. The deadline is today. If you have any questions, please reach out to the sweet young man Malik. He's in the back waving. That's his Discord handle. Apply there, scan the QR code. We good? We good? We're gaming. Alright. Okay, you want to come up here, Michael Vaughn?
Thank you.
Yeah.
All right, so ISTS White Team signups are now open. White Team is the team that runs the competition the day of, so you handle all the questions and you help a little bit with setup and teardown. And honestly, you just get to be in a room with a bunch of hackers from all over the country, so it's very fun. So yeah, signups for that are there. ISTS is March 3rd, 4th, and 5th. That's when you'd be white teaming it up. And yeah, that's about it. So white team signups are there. Do these ASAP if you want to join.
I highly recommend you guys sign up for White Team. It's a very fun time.
It's a very fun time.
Yeah. No responsibilities, but responsibilities at the same time. That sounds like the perfect mix, honestly.
And you get to hang out with.
And you get to hang out with cool people. So, yeah. All right. Meet the sponsors. You know. Come on. You already know. Let's go. All right. Keep going. Oh, yeah. We're so back. We're so back. Okay, stop now. Follow our social media. Sophia keeps it crazy on there. New post coming soon. Follow, please. All right. Okay. So this week we have a very, 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 very sweet presentation. Advanced Windows by Dominic. And it's going to go crazy. It's going to go hard. Don't be scared of the advanced stuff. This is how you learn new stuff. Dom, please come up here. Where are you? Come on, little guy. Everybody give Dom a round of applause, please. You're good. You're gaming.
We're going to run this shit up then, I guess. All right. Advanced Windows. So Mr. Tenshimada gave the original Windows talk last semester, kind of about like what the end user looks like when interacting with Windows. So what this is going to look like is more of the internal side of things. So for those who don't know me, my name is Dominic. I also go by Acrylic. I'm a second-year CSEC student, and this is my first year at RIT. I'm also a red team content engineer and a researcher at TryHackMe, a little bit of an education cybersecurity platform. I also contract as a course instructor with BC Security. So with that, I've been a speaker and instructor at Black Hat USA, Black Hat Europe, and DEF CON. All right, so a little bit about the agenda. We're going to look at authentication for a little bit. Really, we're going to go from what does it look like when we log in, all the way down to what does our applications look like, etc. And then we'll kind of stop a little bit before we get into kernel or kind of hardware things. So you see we're going to talk about a little bit of service functions and routines, processes, and then a little more bringing and incorporating in the authentication and processes. So first with authentication, really what authentication is whenever, say, you want to log into Windows, you may have your little prompt says enter password here, and really authentication is just whenever you hit that enter button. What actually happens? And this is kind of officially more kind of official, just the creating and submitting and verifying credentials through authentication protocols. And so Windows does that by the local security authority, or LSA. And really what this is, there isn't a lot of consensus or great documentation on what it actually does, because it's split into a lot of different subsystems. But really all LSA is a model. Just like any other model, it's just going to standardize some kind of process for Windows. So to log in, like we already said, those protocols are going to be used to handle whatever the heavy lifting is for verified credentials, but the credentials themselves are going to be seen as authenticators, and that's the official language used by LSA. So the things just like plain text credentials, NTLM hashes, PAC, which we'll get into a little later with Kerberos. And so after authentication and the credentials have been verified, the local security authority subsystem service is going to process those credentials and store them in what's called the SAM database, or the Security Accounts Manager database. So one of the most basic forms of authentication for Windows is NTLM, or the New Technology Land Manager. It's kind of just an entire suite of protocols that's going to be used for authentication. And so it's going to be challenge response-based authentication, also known as the Windows NT challenge response authentication. So basically what's going to happen is you'll go ahead and you'll start this entire process by setting just a little bit of information, things like your username, just different metadata to the server to kick off this process. It'll send back some kind of challenge, and you need to be able to prove that you can send your own challenge back to them to be able to compare these challenges and then verify your credentials that way. NetNTLM is also an addition to NTLM that can be used to forward challenges to a domain controller for domain authentication in something like an Active Directory environment, which is seen in a lot of kind of corporate workspaces. So here's just a diagram of kind of NTLM stuff. So here's what I was talking about with, this is what you're gonna send your first information through or your username through here. And then the server, I believe it's a 16-byte challenge that's gonna send back. It's gonna be random. And then you'll have to hash that challenge using your authenticator or your NTLM hash and send it back to the server. And that's what's gonna verify that those two challenges and that response match up. And it's either gonna verify it and send it back to the client and say that's gonna be your local authentication, or it's gonna go ahead and just send all that information over to DC, and it's gonna compare it with its SAM database, which will be the hash, the NTLM hash, which is already stored. All right, so here we see this really old diagram. It's from Windows NT, which is really old. So NTLM is really old. It's a little grandpa of authentication. So that kind of brings us into our next slide of NTLM is at this point considered insecure. It's pretty easy to crack at this point. And so we just generally don't want to use it for Windows. But the thing is, it's still used for local authentication. If you remember, I said that net NTLM is what sends it over to the domain. And so that's why we don't want to use it anymore and why Kerberos was made. Because when sending it over to the domain, there could be a man in the middle attack in which this hash that's sending over to the domain controller can be intercepted and then cracked. So instead, now we use Kerberos, which is just another authentication protocol that's replaced NTLM. So Kerberos uses a ticket system to handle both authentication and authorization. So NTLM was only handling authentication, so it's just verifying those credentials. Instead, Kerberos is going to authenticate using its tickets, but it's also going to say, okay, what resources do you have access to? So a Kerberos, it's going to use what's called the KDC, or the Key Distribution Center, to create a ticket granting ticket. And so this ticket granting ticket is going to be used to kind of determine what resources or service tickets you have access to. And so what the KDC is also known as the KRB TGT, or just the Kerberos ticket granting ticket. So we have these three layers here of tickets to get access to a resource. So the KDC is going to be composed of two different portions, the authentication service and the ticket granting service. These both work, so we'll start off at the AS and we'll go to the TGS. We'll see that a little bit in the next diagram here. So once the ticket granting ticket is received by the client, it's then going to be used along with its authenticator, which is going to be a PAC, or a Privilege Attribute Certificate, along with a session key to verify that this ticket was assigned to me and I have access to whatever you authorize resources I want access to, and I have authorization to have. All right, so here we have a little bit of a diagram. I wish I had speaker notes to just kind of guide me through this. But first, it's going to go ahead and request a ticket granting ticket. And what that really is doing is taking an NT timestamp, and it's going to encrypt it. And then that's what's going to be used, the KDC or the KRB TGT, specifically the authentication service of that, is going to go ahead and try to decrypt that timestamp. And if it can decrypt it, and if that's successful, let's go ahead and send back the TGT. And so really, this is why if you've ever seen, say you're doing something with Kerberos, like Kerberosing, etc., which are a few different attacks, that's why you may see some different time issues of like the server and the client are out of sync. That's why, because it's encrypting the timestamp, right? So after you have your TGT, you're going to go ahead and request a ticket for the actual resource that you want. And then it will, if that's successful, it will go ahead and send back that ticket. And so this is where the PAC is negotiated. After that, you'll go ahead and request a service from the resource server itself. So the KDC has done all that it needs to do, and now the resource server is going and just having another layer of authentication itself with the ticket. And if that's successful, then it will go ahead and send it back to the server. So each one of these is going to be in a request and reply schema. So the top two are going to be an as rep and an as request, or sorry, an as request and an as rep. And the 3 and 4 are going to be a TGS rep and a TGS request. These are something funny, but they're also just a reply and request. So that's just a really brief overview of kind of Windows authentication. So now we're going to kind of move into what happens after authentication. What do processes, applications, etc. look like within Windows? So Windows architecture is kind of split into two different kind of modes here. It's going to be the kernel mode and the user mode, also known as the user land or the protected mode. So really, old Windows used to be a lot more kind of focused on the kernel mode with completely unrestricted access to hardware, modify it as you want, you have any CPU instructions that you want, but really what this ended up with was a lot of crashes. So the problem with the kernel is that if at any point there encounters some kind of bug or some kind of crash, that's not recoverable in any way. The entire system is going to crash. It's not isolated in any way, and that's what ends up with the blue screen of death, if you've ever seen a little smiley face on Windows, right? Yeah. So instead, Windows has completely restricted this to just trusted kernel drivers to run within the kernel. And instead, we've more shifted to user mode, which is going to be limited resources, restricted to a virtual memory address, which we'll talk about a little more when we get deeper into processes. And it's going to be recoverable threads because they're going to be isolated to the process itself and not crash the entire system, right? So like I said, we're going to be focusing in the user land for this presentation specifically because kernel mode is just an entire different realm. So the thing is, even though we have this user mode, we still need a way to interact with hardware, to do things, to interact with the kernel, right? So the kernel is going to use kernel routines, which are just basically functions within the kernel that you can use. But really, within user mode, you have these 5 different kind of sets of calls or APIs, et cetera, that you can use to interact with hardware. And these kind of go in a sequential order of you can interact with one directly, and then there's another one. So Windows API calls are about the most easiest thing to interact with, if you will. So you can just automatically call the Windows API, but really on the back end, what that's doing is the Windows API call is just going to call some kind of NT API. And that NT API call is just going to go ahead and call some kind of system call, which will just continue going down this little stack until it eventually ends up with the hardware manipulating it in some way. So here we kind of see that process a little more in a diagram. So we see our user application at the very top, and then our Win32 API, which is going to be the easiest way that we can kind of interact with hardware. It doesn't do any kind of weird random addressing, at least not that we need to worry about as a more end user. We have this then switching point here where it goes into more kernel mode, and it's going to have your system calls. Like I said, it's going to go from API, usually to NT API or multiple NT APIs, all with different names, to a system call to then the kernel, which will then either impact physical memory or hardware. All right, so again, system calls and NT API are a little weirder, a little less documented, and you can't just import like Windows.h and have access to all those function calls. So instead, we're going to mostly focus on the Windows API and DLLs. So if you have every single application or executable, etc., that you've ever interacted with in Windows has to have some kind of format. Every single file, where it's a PNG, a PDF, etc., it has to have some kind of format, some kind of standard to tell it how it should kind of structure itself. So the portable executable, or the PE file format, is what's going to do this for Windows executables. So it's just going to hold all the information, the data, and the structure for that executable. And this is going to be split into 2 distinct sections. So those are going to be headers, which contain most of the information, the metadata, etc., as well as pointers to different sections within the PE file. And also the session itself, which are what contain the actual data, the actual code, etc., the imports of a file. So here we see a diagram of the PE file. So here we see the headers up top and then the sections. So the headers can split into other headers, and we'll get into that in the next slide of what do each one of these headers actually contain, what kind of pointers do they have, fields, etc. But your sections are split into 3 different other fields. So first, your code section, exactly what you would expect it to be, is just the code of whatever your executable is. That's going to be typically compiled. Your imports, so all the Windows API calls, the NT API, things, this is going to be all of your imports. So things like your MSV, CRT, all of those have to be imported. So say you say printf in C or C++ or any language. Those all have to go through some kind of DLL or some kind of library, some kind of import, and those all are going to appear here through what's called an IAT table or an import address table. You'll also have the data in your section, so things like variables, global variables, etc., are going to be within your section as well. So the headers of the P format are what are a little more interesting because they give us a lot more data, a lot more pointers. They give us something to start with. So each header, like I already said, they can have other headers, and eventually all of them will just have different fields. So the DOS header is part of kind of the legacy backend of Windows. It's just there. It does give us a little bit of information about our file itself. We'll see that in a little bit in the next slide or two. I can't remember which one it's in. But really, this is the DOS stub is one of the most prominent things here, and then something called the E_LFA new, which we'll get into in the next slide as well. But the DOS stub, if you've ever seen like this program cannot run in DOS mode or DOS mode, that's all the DOS stub is. You also have NT headers, which are where a lot more of the interesting information is held. So you have the image file header, which also is sometimes known as the P file header. So it's going to contain information about the structure itself. And you also see the image optional header, which contains a lot of information about kind of the data of the structure as well. And then the section table. So we already know that our sections contain, there's going to be multiple different sections. So .txt, .rdata, .idata, all these different sections, all with different purposes within one P file. So the section table is just going to list every single section within that file and then a pointer to it. So this is kind of how a P file is a very top-down approach in which I can find a pointer from my section table and then jump to whatever section I want. All right, so what really is a P file? So I had this little story of I didn't really understand what a P file was when I first kind of started getting into my research. It made sense that this was some kind of executable, some kind of application, and this was the data behind it actually. But really what we have to understand is that it's just bytes. And so what that originally looked like for me was when I was doing some offensive security research stuff, and we took a payload, a DLL, and we went ahead and put it into XXD, which is just a hex dump utility in Linux. You can take that hex dump, you can put it as a buffer inside of whatever application you're doing for your parsing, and then you can just start at the very first start of your hex buffer and just do math on it. So you can say +4 bytes, +2 bytes, and then it's going to output whatever value of the field or whatever pointer it is. All right, so here we see all the bytes and the offsets of the DOS header or the DOS header. And so we see, say we start at the 0 offset of the buffer, and so we add +12 to that. Now we're at the checksum value, and you can just print that value, print that field and obtain the value. But you may notice that there's not many pointers in this DOS header. So we're going to start our calculations from OX3C. That's also going to be known as the E_LFA new. And so if you'll notice at the very bottom here is the 3C file address of new exe header. And so what that is at the end of every single DOS header, there will be this pointer, and it's going to point all of your other image file headers that then have pointers to all your sections, etc. And so we see how this kind of goes in this cascading effect of this 3C will always be the exact same offset, whereas everything outside the DOS header may not be that same offset, but this will always be constant, and that's what we can work off of. Okay, so we've kind of gone through applications and processes as a form of unmanaged code. So things like C or C++. But there's also this entire other realm of managed code, in which I assume everybody here has taken some form of GCIS 124, or is in it right now, yeah? So in that you use Java, which Java requires the Java virtual machine, right? To go ahead and take whatever your Java code is, compile it itself, and then go ahead and output into native code. So this is really designed so that it can run on any kind of target, any kind of architecture, etc., without the need for different compilation targets, etc. .NET is kind of Windows' solution to this, or Windows application of managed code like Java, and it's a framework for designing Windows applications and services. So instead of something like the Java virtual machine, .NET is going to use the Common Language Runtime, or the CLR, to compile directly to machine code. So what it's going to look like is you'll have whatever, .NET is just a framework. It's not a specific language. So whatever language is using the .NET, will go ahead and be compiled into what's called the Common Intermediary Language, or the CIL, which will then go ahead and at runtime, it will use what's called, it will just in time compile it to go and compile into native machine code. And so this means any kind of target, it's all common, so it goes down to one target. So like I just said a little bit in the previous slide, it will use a just-in-time compiler, or a JIT compile, to go ahead and compile that intermediary language to machine code. And so the goal of it is just to be consistent across multiple languages. So there's things like C#, J#, F#, Visual Basic.NET, and Boolean. So all these different languages have this common ground of, even though they have different syntax, etc., they all can go ahead and ultimately be the same instructions natively. So just again, we see the CLR, or the Common Language Runtime, goes ahead and compiles into the Common Intermediary Language, which then gets compiled at runtime for a just-in-time compiler, which then gets compiled into native machine code. So here we see this as a diagram. So at the top we have whatever our language is, and then this assembly code will be what our CIL, or our Common Intermediary Language, is. Into the CLR, the GIT compiler, into native machine code, which can then run on the operating system. So because there is some kind of middleware here, there is something in the middle of whatever these operations are for compiling this code, there's a lot of area here to put things in the middle. And so that means that there's a lot of security implications for defenders or for attackers with two kinds of technologies here called ETW and AMSI. So event tracing for Windows is tracing logs raised by either user mode applications or kernel mode drivers. So here we're obviously looking at user mode applications that are managed. So ETW, that's any logs really at all in Windows, unless it's some kind of application-specific log. It's going to always be logged within what's called the event viewer. So any kind of log that you see within Event Viewer, that's all handled by ETW, which has different kinds of own technologies by itself, which could be an entire presentation for consumers, producers, etc. And so ETW, because we are going and we have some kind of thing in the middle between our code being compiled and our code being executed, this means that that can be placed right in the middle of it and can intercept all that. And so that's especially prevalent with AMSI, or the Anti-Malware Scan Interface, which kind of provides this vendor-agnostic, very standardized interface to allow applications to integrate with quote-unquote anti-malware products. It's not very clear what those anti-malware products actually are, what they do, although we have some information. So as the code is being compiled, and before it can even execute, it's going to go ahead and scan this code. And so within the CLR. And so that's going to do file and memory or stream scanning, which is going to be, if you say like Windows Defender, and then you try and execute an application in the CMD, and before it even executes, it's going to say this program has malicious content or something along those lines. That's mostly because AMD is going to catch that before it can even compile and before it can even execute, right? Within the CLR. It can also do content source and URL IP reputation checks. I haven't really seen that in Defender. This is just something that Windows on their documentation says it can do. I haven't really seen that. And they also say that it has other techniques, but I also haven't seen any of those either. Okay, so now we kind of have our understanding of some kind of language, how we're going to interface with the internals, how we're going to log in, etc. Let's go ahead and kind of shift gears over to processes. So a process really is just going to maintain and execute any kind of application. So our our application is going to be whatever you see as an end user within your kind of interactive session. A process is what an application is actually going to mean to the internal backend for Windows. So applications at their core are kind of metadata, kind of just information about some kind of application, but they do a lot more than that as well, which we're going to see on the next slide. So there's going to be a virtual address space. So processes, like I said, to prevent crashes, etc., they're all going to have their own separate section of virtual memory, so they're not going to get physical address space. And so that's going to kind of prevent and kind of contain any kind of potential crashes, corruptions, etc. Obviously, the code, the security context, what privileges the process have, a unique identifier, It's going to be handles to the objects as well. So that's going to be how we can use and manipulate the process or a handle on the process in code. There's also going to be environment variables. So every single process, if you've ever seen your like $env, all of those are going to be added and stored in every single process, not just globally. And then every single process needs at least one thread of execution, if not more. And so that thread of execution is going to allow you to actually execute the application rather than just be the metadata of the application. So in memory, there's going to be obviously the code, the global variables, and just a lot of kind of storage and resources for this process. Then there's also an environment block and then all of your threads. So this is the entire section of virtual memory that the process has. But can anybody kind of spot what may look a little strange here, or what might not be a little more obvious when just looking at code? So there's an environment block, which is very specific to processes and threads. So really what the environment block is going to hold all of the information for a currently running process. All of the data, all of the imports, all of its, sorry, I blanked. But all of the information on the currently running process is going to be held in this process environment block, or this PEB. The PEB will also have an E process or an executive process, which is going to define some of that structure. ETW can also reside within the E process. So if we're not dealing with managed code and it can't be within that CLR, it's going to be within the E process as well. So the E process is really just going to be a kernel representation of a process. And then K process, or the kernel process, is also going to be a subset of the E process. So that just kind of holds a lot of information. We'll look at this a little more, but there's also going to be the loader, or the LDR. And this is going to be kind of what loads all of your DLLs, all of your imports, all your libraries, things like kernel 32. We'll see a little more about what all imports later for every single application. But this is going to have, it's going to be stored in a linked list format. So you have different kind of orders in which you can look at these linked lists to kind of see as they load into this process. So on the right, we see the structure of the PEB. And so we see things like being debugged, NSA private key, LDR, a few processes, but we also see a lot of reserved. And that's a little weird to me. Why isn't Windows just like telling us what's in the structure? You know, why not? So this doesn't make me very happy, you know, because like I would like to know what's actually running in this structure. So what we're going to do is we're going to do a little, hopefully you can see this. We're going to do a little debugging. So this is a tool called WinDebug. It's a pretty common application debugger for Windows. It's completely command dependent. There isn't really much of a GUI here. Oh, that just, I don't know what this, okay. This should be fine. Oh, this went, okay. All right, so here we're just going to dump the PEB. So WinDebug has a special command, !PEB, that will allow you to stylistically kind of dump the PEB. And so we see a lot of kind of information here that it's skipping it again. Okay. All right. So we're going to see a lot of information here. You can't actually see that. But what that says is image base address. And then under that, or above that, I'm sorry, we also see being debugged. Being debugged was also we saw that in the original structure as well, that Microsoft actually publishes. But we also see all this other information here that Windows doesn't publish. So we see things like the image base address, we see a base address for the LDR, and also all these here, you probably can't see them, but those are every single module that's loaded by Windows. So things like NTDLL, kernel 32, Win32, GDI32, all loaded by Windows. Here as well, we're going to dump the, sorry, this is the same thing over again. Okay. So here we're going to go ahead and dump the NTDLL of the PEB. So within NTDLL, it's just going to have all these structures for Windows. And here we see the entire PEB structure within NTDLL, and you can't actually tell what those words are, but there's a lot more structure here than what Windows is publishing. There's probably like 3 times as many different pointers and offsets and functions that you can use here. And so this is just all the information surrounding a process. And all of these can be used within code to go ahead and get different information about a process. Okay. Okay. So here what we're going to do is just, you'll probably not be able to see this either, but what we're going to do is dump the PEB again. We're going to get our base address for LDR, and then we're going to use this. It's a linked list. So we're going to go ahead and use the structure PEB underscore LDR underscore data, which is going to have all the data for the loader as it's loaded. So every single process will have this loader buffer here. It will then have the very first offset or pointer for the linked list, which we're going to dump with LDR underscore data underscore table entry with the pointer to whichever order we want or whichever linked list we're going to follow. And so here we see that we have a linked list entry. And so this is going to be the entry for the application itself, notepad.exe, and a bunch of other information with that module as well. And then what we're going to do is we're going to copy the linked list pointer again to the next node, and then that will open ntdll.dll, I think. Yeah. So here we see another node, which is ntdll.dll. And so you can continue following this just like the stylized exclamation point PEB command. That's just Windybug really doing all this kind of linked list pointer gathering for you, right? So this is really just something cool that you can do with processes. It doesn't have a lot of implications unless you get deeper into security research. So one of the components of my research that I'm doing is a lot of EDRs go ahead and will inject some kind of DLL as that it will hit before it can load the legitimate DLL. So something like kernel32.dll, it will inject it before, it will place a jump before the actual kernel32.dll. And so whenever it's going ahead and loading all these linked lists, it will go ahead and hit that, load that kernel32, and all your API calls, all your functions, etc., will go ahead and be triaged by the EDR. And so it's going to hit their functions instead of the actual function, right? And so what some of my research is going and doing what's called PEB walking. And so I go ahead and go through all this linked list in my code, and you just go to the actual kernel32.dll instead of being tripped up by their loaded kernel32.dll. And so that's a little, kind of, one little cliff right there, but it's fine. Love you, Kenny. All right, so process threads. So like I already said, threads are going to be what's actually executing whatever kind of code, whatever kind of data imports are here, and they're going to be scheduled based on device factors such as the CPU, memory specifications, whatever priority it has over other execution threads, logic, etc. And so there's a lot less components here than kind of processes, but there's going to be a stack, thread local storage, kind of go ahead and store any information, any data from the thread. And there's also going to be a context structure, which is going to go ahead and give us access, kind of like handles for processes. It's going to go ahead and give us a lot of kind of information about the thread we can go ahead and get within a code. So kind of a general, not necessarily a theory, but just a general statement is that every process for a user is a thread for a kernel. It's not necessarily true, but it's kind of just this general idea that you can think of when comparing processes and threads and how they interact with the user mode and with the kernel. So with processes, they go ahead and each one of them has a virtual memory space, whereas with threads, each one of them is going to share whatever memory space that process has between each thread. Just like there's going to be a process environment block, there will also be a thread environment block, which just like the process that we saw, is going to just hold all of that information. And there's also going to be a thread information block, which we're kind of diving into a lot of the undocumented territory here. So it's very unclear if thread information block if you actually look up the acronym TIB, you won't find it anywhere, but you have to look up the actual thread information block. And there are resources for it, and it is kind of documented, but it's very unclear what it actually does, and if it's a subset of the thread environment block, or if they're the same thing. I don't know. I'm going to say that they're the same thing for now, but as other things. Okay, so here we see that there's, again, a lot of reserved things. So now all they give us is the process environment block and some TLS stuff that I don't really care about. So again, this makes me a little angry. I don't like it when stuff is a bunch of reserved. So we're going to go ahead and dump it again. So instead, we're going to use exclamation point TEB. We're just going to go ahead and dump the thread environment block. And again, you probably won't be able to see this very well. But there's different information like the stack address, fiber data, the client ID. So there's going to be all these different pointers and offsets that you can go ahead and use to get information about a thread. So here again, we can go ahead and dump the structure for the TEB from NTDLL. And here we see this exact same structure that should have been on the Windows Microsoft documentation, but is not there. So we see things like client ID, Win32 thread info, WoW32 reserved. And so all this information you can use for threads, use within your own applications, etc., that just isn't documented by Microsoft. So there's a bunch of cool things you can do internally here. Okay, so there's a few kind of security considerations when it comes to processes and threads. Because these are in memory, there's a lot of kind of volatility there. And so data execution prevention, I'm sure a lot of you guys have probably heard about some of this stuff within your own kind of CSEC courses, etc. But that's just going to mark most of your pages as non-executable, mitigating buffer overruns, overflows, etc. But just marking everything as non-executable unless it's specifically marked as executable by the application. There's also address space layout randomization, or ASLR, which is just going to randomize all the addresses of processes and DLLs. So before ASLR was kind of implemented, all the API calls, all the functions, all the NT API, etc., for Windows, they all had constant addresses that you can just go ahead and say, this is the address that I want. Now instead, they're all dynamic. So if you've ever, say you're coding in C or some language that's using the Windows API, if you've ever seen you're importing Windows.h, what that Windows.h is a loader to go ahead and load go ahead and find all of these addresses for you, load all the structures, etc., and do all that heavy lifting for you. So now that we've kind of covered a little bit of authentication, a little bit about how we're going to interact with internals, and then the internal side of processes and threads and how applications look, really, I think, do you remember I kind of mentioned the security context of a process and of a thread. So really that security context is going to be determined by tokens. And so very similar to kind of something like a web application token or a cookie. These are going to be created at login for every single user using their password, their NTLM hash, or some form of impersonation, which we'll kind of cover a little bit later. And that's going to be created for every single user that ever logs in. And then a process by default is going to use the access token of the user that logs in, or it's going to use its parent process token. And that's how it's going to determine what kind of privileges it has, what kind of permissions, and what security context it's running. A thread then will use a copy of its parent process as its token. And so the copy here is what's really important because when using these tokens within a thread, because they're not copied, if you modify that token at all, that's going to modify the token for any process in any thread using that token because it's not a copy. And so that's where a little bit of the impersonation comes in, which we're going to expand on a little bit in the next few slides. All right, so here we see Mr. Anderson is attempting to log into Windows with his little username. LSA, like we said, is going to handle all the authentication things, send it to the DC if necessary. And then what's going to do is go ahead and provide Kenny with an interactive log on session, which is what you're just going to see the normal Windows desktop, etc. And this is all going to be within Windows Station 0, which is just kind of the default station for Windows. I didn't really cover a lot of that this talk, but the previous year's talks have gone over that. I would encourage you to go ahead and watch those because you'll kind of figure out a lot of stuff about the Windows Station, etc., and some of the more formal structure for Windows. But along with the interactive logon session, LSA will also go ahead and create an access token. So instead of going ahead and for every single process, every application that you want to run, instead of making you re-input your password or your hash, etc., it's just going to use this access token to do all that for you. So there's kind of 3 different security or access tokens here. So there's a primary token, and so that's what we just created when Mr. Anderson logged in. And so it's just going to define the kind of user context and the permissions for that user, and be used by any kind of process. And then there's also going to be a restricted token. So unlike the primary token, the restricted token is going to have limited privileges and permissions for most user applications that are non-Windows native applications. So things like Google Chrome. And so this kind of implements the kind of principles least privilege, and they can either be created during process creation or by using the Windows API. I think it's create restricted token. There's also going to be an impersonation token, which is going to be part of an impersonating thread, or a thread that is copying the token of a process or another thread. And so there would be the primary token, which is going to be a copy, and then there would be an impersonation token for this entire impersonating thread. So say you have something like SMB, something like PSExec, where within a client-server model, there's a lot of different threads that want to go ahead and connect to the same resource. If one of those threads wants to change something within them, we don't want that to change it for everything, right? So that's why we're going to use the impersonation, create a copy of the token, and then describe the context of the impersonate client. So it's going to have all the same privileges. It's going to be the same token. It's just going to be a copy of it, an impersonated token, instead of the actual primary token. So things like multi-thread applications, network authentication, they're all going to mostly use the impersonation token. So here we see again, we're authenticated with Kenny. Explorer.exe, which is a native Windows native application, is going to use the primary access token, and then cmd.exe is going to go ahead and use the access token of its parent process, so Explorer.exe. So these will be the same 2 tokens. And then we see we're going to deploy the Gumper, which is then going to use a restricted access token. So it's going to use a restricted access token because it's not a Windows native process. So this is only going to give it read-only permissions, and it's going to compare that with the security descriptor of a file to go ahead and compare those 2 access and see, okay, can this Google Chrome application actually go ahead and read this file? So tokens also have some special privileges that can be assigned to them apart from the kind of generic read, write, execute permissions. So these are going to give them access to other kind of system resources or tasks. You'll see here that, say, a token has the SE shutdown privilege that can go ahead and just shut down the system. It has a permission. It doesn't need any kind of administrator rights, access privileges. It can just do that with the token it already has. We'll also see an interesting kind of token at the bottom here, the SE impersonate privilege, and that's going to allow it to create an impersonated token or impersonated thread. And so this, it's for any user or any token that is already on the system that is authenticated. So even if you're an underprivileged user, you can still go ahead and impersonate that token even if they have higher privileges than you. So just kind of wrapping it up here, we've kind of looked at how processes they go ahead and interact with the internal side of Windows. Also seeing how they kind of interact with authentication. So there's this other concept here where they're communicating between each other. So say you want your process to go ahead and not use common network protocols, etc. That's where inter-process communication, or IPC, is going to come into play. And so that's going to be able to communicate through either shared memory. So they're going to have 2 sections of memory that are shared, and they can go ahead and pass messages through that. Or they can do message passing, which is going to be a lot more like your formal network protocols, etc. So Windows kind of solution to the inter-process communication is going to be Windows pipes. So pipes are going to use a shared section of memory to communicate. So like we said, instead of message passing, they're going to be communicating through that shared piece of memory. And they're going to either connect to a pipe server or write to a pipe client. So so even if 2 kind of devices or 2 processes are on two completely different networks, two completely different devices, they can still go ahead and share memory, and there has to be some kind of mediator there for them to do that. But they can go ahead and share memory and just communicate that way. There's going to be two kind of different pipes here. One being the name pipe, which has to have an identifier for it. That could be one-way or duplex communication, so going both ways. And so this then allows that kind of communication between two completely different devices. So something like PSExec, that's going to use name pipes. The kind of downside of this, even though it is duplex communication, it requires that to be predetermined on both sides. There's also unnamed pipes, which are going to be anonymous and one-way communication. But though the downside of this is that they can only be local communication. So just kind of wrapping up this presentation here, we've kind of taken a look at starting from the Windows login, how can we authenticate, how do applications look like within Windows internals, and then just very briefly kind of how those can then be interacted with and go down to hardware and how we can interact with the internal side of Windows with languages. And so hopefully, even though we didn't get a lot of the kernel side, a lot of the I/O layers, etc., hopefully that allows you to kind of interact with those and understand what's happening on the back end from the user mode perspective a little more. All right, so any questions? Yeah.
Does running the process as admin create an impersonating token or primary token? Or like
Yeah, so it's a primary token.
and that goes through LSA?
Yeah, so basically what's happening is there's the whole other thing of UAC. So basically, impersonating is creating a copy of a token for something that's already authenticated. And so assuming that's a Windows native application, it's going to go ahead and authenticate again using that, whatever those administrator privileges are. That's going to create that token. So you already have to have those administrative privileges, and then it's going to inherit those privileges from the token, and that's what you're going to use as the primary access token. Mr. Kennedy is telling me I'm out of time.
No, you did pretty good. You have like 10 minutes, but I mean, I'm going to kick you off anyway because you kind of were behind. We're gaming. We're gaming. Oh, we're so back. That was great. Everybody give Dom a round of applause.